the proofs. The first theorem is if A is equivalent to C, B is equivalent to D, A intersection B is empty, C intersection D is empty, then A union B is equivalent to C union D. So let's assume all that stuff. Assume. Now, what does this mean? Well, because A is equivalent to C and B is equivalent to D, we have a mapping from A to C that's 1 to 1 and onto. Let's call it F. And there's a mapping from B to D that's 1 to 1 and onto. Let's call it G. Now, I need to create a mapping from A union B to C union D. And that's going to be FUG, F union G. We already know it's a function because we proved that before, since A intersection B is empty. So now I just need to prove that it's 1 to 1 and onto. So first, onto. Let Y be an element of C union D, the codomain. Well, it's either in C or it's in D, but it's not in both. If Y is in C, then there exists some X in A such that F of X equals Y, since F is onto. Well, that means that F union G of X equals Y. Similarly, if Y is an element of D, there's some X in B that G maps that X to Y. Did I do that right? Yes. So F union G of X equals Y. Either way, it's in C or it's in D, we have something that gets mapped to it, so F union G is onto. Next, we need to prove 1 to 1. This is a little bit stinkier, harder, whatever. Suppose F union G of M equals F union G of N. So how are we going to go at this? I'm going to look at the output. So F union G of M is either in C or it's in D. If it's in C, that means F union G of M is actually just F of M, because that's the part of the function it comes from. I also know that F union G of N must be in C since they're equal, so F union G of N is F of N. Now I can say that F of M equals F of N, and since F is 1 to 1, M equals N. Similarly, I can do the same thing if F union G of M is in D. Go through the same steps but use G instead of F. Therefore, I have F union G is 1 to 1, which means I have a 1 to 1 mapping from A union C to B union D, which means they're equivalent. You lost the bottom of the page. Apologies. Okay. The next theorem. Let's see if I can do a better job of keeping it on the page here. Suppose A is equivalent to C and B is equivalent to D, then A cross B is equivalent to C cross D. I will assume that A is equivalent to C and B is equivalent to D. So I have a mapping that's 1 to 1 and onto from the appropriate sets. F goes from A to C, G goes from B to D. I will construct this function, F cross G. That's my new symbol for it, and it's defined to take the order pair A comma B to F of A comma G comma B. Yeah, this right here that I can't pronounce because I'm getting tongue-tied. Now, one of your assignments is to prove that that is a function. That's one of your dailies. You also need to prove that it's onto. That's another daily. And you need to prove it's 1 to 1. That's another daily. So since this function is 1 to 1 onto, then A cross B is equivalent to C cross D. Next theorem. If A is finite and A is equivalent to B, then B is finite. Assume A is finite and A is equivalent to B. Well, if A is finite, it's equivalent to n sub k for some k. And since we know that this is an equivalence relation, I know that B must also be equivalent to n sub k, which means B is finite. Lemma. This basically says if I add one element to a finite set, its cardinality goes up by 1. It'll have one more element. I shouldn't say its cardinality if it's finite, it goes up by 1 element. So suppose S is finite. The cardinality of S equals k, and X is some element not in S. Then S union the set containing x, the cardinality of that is k plus 1. So what I need to do is construct a function, or that's how I did it before, but I'm going to use what we've already proved to make this a whole lot easier. Okay, suppose S is equivalent, the cardinality of S is k, and x is not an S. Well, I know that S is equivalent to n sub k, and x, since it's only one thing, is equivalent to the set containing the number k plus 1. Unioning, and I know that S intersection x has nothing in common, n sub k and the set containing k plus 1 have nothing in common. So I'm going to use that first theorem to show that, to be able to say that, well, that means S union x, the set containing x, is equivalent to n sub k union k sub 1, which is just n sub k plus 1. Therefore, the cardinality of S union the set containing x is k plus 1. This is a whole lot easier way of proving it than whatever they did in the book. And now I want to prove that every subset of a finite of n sub k is finite. Let k be an element of the natural numbers and a be some subset of n sub k. We're going to do this by induction on k. So first, if k equals 1 and a is a subset of n sub 1, that means a is either empty or a equals the set containing 1. Either way, a is finite. Assume this is true for some k. So that means every subset of n sub k is finite. I want to prove it for k plus 1. So I want to show that every subset of k plus 1 is finite. Assume a is a subset of n sub k plus 1. Well, if k plus 1 is not actually in a, then a is a subset of n sub k, which means a is finite. So now what if k plus 1 is in a? Well, I'm going to pick it off. I'm going to note that if I remove that element, a minus that element is still going to be is now a subset of n sub k, which means it's finite. By the previous lemma, if I add an element that's not in a set to the set, it's still finite. So a minus k plus 1 union the set containing k plus 1, that's finite. But a minus the element, adding it back in, is a, which means a is finite. So every subset of n sub k is finite. Now I'm going to use that to show that every subset of a finite set is finite, not just n sub k. Ooh, make sure I get it in here. Suppose S is finite and T is a subset of S. If T is empty, T is finite, we're done. So from now on, I'm going to assume T is not empty. So since S is finite, there is a mapping F going from S to n sub k for some k in the natural numbers. If I restrict that mapping to just T, going from T to f of T, I know it's 1-to-1 because the restriction of a 1-to-1 function is 1-to-1. I know it's onto because I chose f of T, which is the image. It's literally everything that f of T spits out. So this is a 1-to-1 onto mapping, which means T is equivalent to f of T. F of T is a subset of n sub k, which by our previous theorem means f of T is finite. Since f of T is finite, T is finite. So we know that the subset of any finite set is finite. Now let's talk about putting sets together. It should make sense to you that if you take two finite sets and stick them together, they're still going to be finite, which is true. So let's look at this proof. If A and B are finite disjoint sets, that means the cardinality of A union B equals the cardinality of A plus the cardinality of B. So we're going to assume that A and B are finite disjoint sets. That means A is equivalent to n sub m, and B is equivalent to n sub n for some m and n in the natural numbers. In other words, the cardinality of A is M and the cardinality of B is N. Well, clearly n sub n is equivalent to this set, m plus 1, m plus 2, yada yada yada, up to n plus n. You just add m to all the elements. Also, m plus this set here, intersection n sub m, is empty because I started after the last element of n sub m. So again, using that previous theorem, A union B is equivalent to n sub m union the set I constructed, but this is the same thing as n sub m plus n. A lot of m's and n's. Okay. Now what about the cardinality? Well, A union B is finite because it's equivalent to n sub m that thing. And the cardinality of A union B is m plus n, which is the cardinality of A, plus the cardinality of B. What if they're not disjoint? Well, then you toss out the section that's disjoint, where they overlap, and add it back in. You create disjoint sets, so I can use my previous theorem. If A and B are finite, then the cardinality of A union B is the cardinality of A plus the cardinality of B minus the cardinality of the intersection. So A minus the intersection of A intersection B and B are finite disjoint sets because I tossed out the part where they are equivalent. Where they overlap. The cardinality of A minus A intersection B is the cardinality of A minus the cardinality of A intersection B, because you're just removing those elements. Which means the cardinality of A union B is the cardinality of A minus A intersection B union B, which is the same thing as the cardinality of A minus A intersection B plus B, the cardinality of B. That's a mouthful. Okay, so, but that is the same thing. The intersection of this guy, getting tongue-tied. So this guy, I said, was equal to this thing. So if I'm going to replace that with that, and rearrange a little bit, I have A here, I have minus the intersection here, and I've got B here, which is what I'm trying to prove. If A1 through AN are finite, then the union is finite. It's key that there's a finite union of finite sets. Suppose A1 through AN are finite by induction on N. If N equals 1, you only have one set. It's finite. We're done. Assume it's true for some N. In other words, if I have a collection of this N of finite sets, the union is finite. So let's look at N plus 1. Suppose A sub 1, yada yada yada, A sub N to A sub N plus 1 are all finite. Well, I know that the union of A1 through AN is finite. This is a finite set once we've unioned them all together, and this is a finite set. So now I just have the union of two finite sets. And I know the union of two finite sets is finite by the previous theorem on the other page. So the union of all of them is finite. Next one, lemma. I'm going to need this to prove the pigeonhole principle. So let R be an element of the natural numbers where R is greater than 1. If X is some element of N sub R, then if I remove that element, it's equivalent to N sub R minus 1. So basically we're saying that if you take one away, it's one less. It's just kind of like a duh, but we need to prove it. Suppose R is an element of the natural numbers and R is greater than 1, and let X be an element of N sub R. Now, we need to create a mapping from here to here. And I have a little picture over here in pink that might help. But let me do this here. So let F be a mapping from N sub R minus X to N sub R minus 1. So this represents N sub R minus the X. See, I got 1, 2, dot, 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 dot. The X here is missing. So what's going to happen is anything less than X gets mapped to itself. Anything bigger than X gets mapped to one less. So that's what this mapping is. So f of k equals k. If k is less than x, it's k minus 1. If k is greater than x. Clearly, I can see this is 1 to 1 and onto, which means n sub r minus the set containing x is equivalent to n sub r minus 1. This is a really cool one. Okay. This is the pigeonhole principle. Did I write that it's a pigeonhole principle?